All right, hello and welcome back. In this video, we're covering section 6.2. So we're going to look at the trigonometric functions again, but this time in relation to the unit circle. So we're going to build out the unit circle. And we took a slight detour last time into 8.1, where we defined the 6 trigonometric functions in terms of a right triangle. So just as a quick recap, we have a right triangle, and we say that this is some angle theta. Then this would be the side opposite of the angle. Then this would be our side adjacent. And then this is our hypotenuse. And so we defined the 6 trigonometric functions. So the sine of this angle theta, the cosine, and the tangent. Define the sine of an angle as the opposite side length over the hypotenuse. The cosine as the adjacent side length over the hypotenuse. The tangent as the opposite side length over the adjacent side length. And then we had some reciprocal functions. So for the sine, its reciprocal is the cosecant. So that's the flipped version of the sine. We can write it as the reciprocal. The cosine's reciprocal is the secant. So that's 1 over the cosine. And then the tangent has the cotangent, which is 1 over the tangent. So we defined all this last time. If you haven't already watched that video on 8.1, I would highly recommend that you take a look at that first, because we're going to be working out of that context in order to build out the unit circle in this video. So let's go ahead and first define the unit circle itself, how we're going to define it. All right, so the unit circle, as the name implies, it's a circle. This is the circle that's centered at the origin. So this is the point 0, 0. So it's centered at the origin with radius 1. And as we'll see, this is going to produce some very useful properties in terms of our trigonometric functions. So let's visualize. Let me get a circle in here. So we imagine we have our circle. This will be the center point 0, 0. And so if we put some random point up here, and this will be some x coordinate and some y coordinate, we can draw an imaginary line, and that will be the radius. So we've defined this as a radius of 1. So with any point on a circle, you can imagine dropping down a straight vertical line from our point and then sending out a horizontal line until they meet, and they're going to meet at a right angle. So we actually get a little triangle inside of the circle for any point on a circle. And if we think about what the side length should be, since we're starting at the origin point here, this would just be a distance x. That's the horizontal distance defined by our x coordinate. And then this will be a vertical distance y. So let's extract this out. Let's look at this triangle on its own. We have some triangle, and let's call this angle theta. So you can imagine this is some angle. It's in standard position. It's starting on the positive x-axis, rotating counterclockwise, and then wherever the angle terminates, it creates a point on this circle. So we can associate any angle with some point on the unit circle. That will be useful as well. So we said that this triangle has a side length on the bottom of x. This is a side length of y, and the hypotenuse is 1. So let's use our right triangle trigonometry to define a few things here. And remember, we were using the acronym SOHCAHTOA, SOHCAHTOA. Say the sine is the opposite over the hypotenuse, the cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. So that means on this triangle, the sine of the angle, so the sine of theta, is the opposite over hypotenuse, so the opposite would be y, and our hypotenuse is 1. So y over 1 is just y. And then we can do a similar thing for the cosine. We can say the cosine of that same angle is the adjacent side, which is x, over the hypotenuse, which is 1. X over 1 is just x. So this produces a very useful property. When we're on the unit circle, any coordinate point, x comma y, well, we just said that x is equal to the cosine of theta, and y is equal to the sine of theta. So this is specifically a point on the unit circle. This wouldn't be any point anywhere, just a point on this circle. So that means any coordinate point on the unit circle gives you, just by looking at the point, the cosine and the sine of the angle that produced that point. So let's draw a second circle just to illustrate that. So we still have our center at 0, 0. Now our random point, instead of x comma y, I'll write cosine of theta, sine of theta. We still have this side length being 1, that's the radius of our circle. And we can imagine this triangle produced where this x distance is the cosine of the angle producing this point, and then the y distance is the sine. So from this we can get two new identities. We were looking at a few identities last time. Let's first think about the tangent. Well, we said the tangent is the opposite side length over the adjacent. So in this case, that would just be the sine of theta over the cosine of theta. So this gives us our first, we'll call this a quotient identity. I can remember how to spell identity. So it's called a quotient identity because we're taking this quotient, doing a division. So that's good. And then let's also remember the Pythagorean theorem. If we did it on this first triangle, we would get x squared plus y squared equals 1 squared equals 1. That's actually the equation of the unit circle. The circle centered at the origin with radius 1. Down here, when we think of it in terms of sine and cosine, we can say one side length squared plus the other squared equals the hypotenuse squared. Usually start with the sine for whatever reason. We can say the sine squared of theta. You'll usually see it written out this way with the square here attached to the sine. I think the main point with that is if we placed it over here, it might be confusing whether this square is applying to the angle or if we're looking at this whole thing squared. And sometimes in text, they won't even write the parentheses around the angle, so it can be confusing. So to sort of avoid that misconception, usually write the power next to the trig function to apply that. This is the sine of theta, the quantity squared. So that's one side length squared. The second side length we're saying is the cosine. So sine squared plus cosine squared equals 1 squared, or just 1. So this is another very important and very useful identity. We can call this a Pythagorean identity. And these come into play, as we'll see later. A lot of times we want to express things in terms of the sine and the cosine. So a big part of learning these identities is learning how to change one expression in one trig function into something with just sine and cosine. And we'll see why that's useful in a little bit. But the main point here is that on the unit circle, any coordinate point that we can establish will give us the cosine as the x coordinate point and the sine as the y coordinate point of the angle that produces that point itself. And that will become very useful in trying to determine what the values of some common angles around the unit circle are. And we took a look at some of those common angles back in 6.1, if you recall, going around the circle. So we will revisit that and add some coordinate points this time. So let's start building out some angles that we can find on the unit circle. And the easiest ones to derive are going to be the quadrantal angles. And if you remember, those are the ones that occur in between the quadrants. So let's place another circle here. So this is our unit circle centered at the origin. So let's imagine this is the y-axis, and this will be the x-axis. And the 4 quadrants, we start with quadrant 1, where x and y is positive. Then we go counterclockwise. This is quadrant 2, where x is negative, y is positive. Then down to quadrant 3, where both x and y are negative. And then quadrant 4, where x is positive and y is negative. And so that same idea applies to the sine and cosine. Since we're relating the cosine to the x coordinate, we can already know that the cosine should be negative in the second and third quadrants. Whereas the sine, since it's associated with the y coordinate, will be negative in the third and fourth quadrants. And that's for angles that terminate in those quadrants. So already some useful information. So we know that we're on a circle of radius 1. So we can get these 4 points pretty easily, just thinking, well, this is an x distance of 1, y distance of 0, the point 1, 0. And this would be associated with an angle of 0 radians. Or if we were going all the way around, that is an angle of 2 pi radians. So those two are coterminal. And as we'll see, coterminal angles share the same trigonometric values, because since they're going to produce the same points on the unit circle. Then up here, well, if the whole thing is 2 pi, half of that should be pi, so that's over here. It's like 180 degrees. This has the coordinate point negative 1, 0. So that already tells us we'll have, and keep in mind, each x coordinate is the cosine of the angle, and the y coordinate is the sine of the angle. So that already tells us for pi, the cosine of pi should be negative 1. The sine of pi should be 0. Just thinking about those coordinate points. So if this is pi, then half of it will be pi over 2, half of pi. and we're on a circle with radius 1. This distance is 1 as well, so that would be the coordinate point 0, 1. And that's the cosine and sine of pi over 2. And if that's 1 pi over 2, then we have 2 pi over 2, so this would be 3 pi over 2, just to show how I remember what these angles are called. So this is 3 pi over 2. So this will have a coordinate point of 0, negative 1. So keep this in mind, that on the unit circle, the x value is the cosine and the y value is the sine. And let's take a look at some examples here. So it's saying to find the exact values of the 6 trigonometric functions for each of these quadrantal angles. So we'll start with 0. I'll say when theta equals 0, let's see, where are we on the unit circle? Well, we are basically at the starting point. We haven't moved at all. Over here, the coordinate point is 1, 0, because the radius is 1. So let's just use that fact, and I'll write it up here again, that the x-coordinate is the cosine, and the y-coordinate is the sine. And we'll be able to start listing off our trigonometric functions. So the sine of theta, when theta equals 0, is the y-coordinate here, so it's going to be equal to 0. The cosine is equal to the x-coordinate, so that will be equal to positive 1. And then the tangent, recall that we were able to define this as the sine over cosine, sine of theta over cosine of theta. And that's true just in general. So we can just take these coordinate points, take the y-coordinate and divide the x-coordinate. 0 divided by 1 is 0. So the tangent will be 0 for an angle of 0. So let's get the rest. We have also the secant. The secant is defined as 1 over the cosine, or the reciprocal of the cosine. So if the cosine is 1, we can think of that as 1 over 1. The reciprocal of that would be 1 over 1. So that's equal to 1. How about the cosecant? Cosecant is 1 over the sine. The sine is 0, so that's 1 over 0. And anytime we define by 0, or we divide by 0, we get an undefined result. So notice some of the trig functions can give you undefined results. They're not defined everywhere. And particularly for the reciprocal identities or the quotient identities, anytime you have a trig function in a denominator, anywhere where that trig function is equal to 0 will produce an undefined result. All right, we just need to add the cotangent. So cotangent is 1 over the tangent. Here the tangent is 0, so we also get undefined. So keep an eye out for those. All right, let's look at B for pi over 2. This was 90 degrees. So part B, you can say when theta equals pi over 2, I can think again, where am I? Well, I'm up here at 90 degrees. That will have a coordinate point of 0, 1. So just by looking at it, I know the sine should be, the sine of pi over 2 would be the y-coordinate, so 1. The cosine of pi over 2 will be our x-coordinate, which is 0. The tangent will be sine over cosine, so 1 over 0, that will be undefined. So the tangent can be undefined as well because we're defining it as a quotient. So anywhere the cosine is equal to 0, the tangent will also be undefined. So let's put the rest. We can say the cosecant is 1 over the sine, so 1 over 1. It's equal to 1. The secant is 1 over the cosine, 1 over 0. That will be undefined. And then the cotangent is 1 over the tangent. The tangent was 1 over 0, so the cotangent will be the reciprocal of that, 0 over 1. That'll be equal to 0. So that was for pi over 2. Next, let's look at pi. This is part C. And say when theta equals pi, or 180 degrees. Draw a quick sketch. We're over here at the point -1, 0. So that'll be useful. So let's go through again. We can say the sine of theta, whenever theta is equal to pi, or 180 degrees, will be 0, the y-coordinate. The cosine will be -1. So these values can be negative because we'll be in negative parts of the quadrants. The tangent is sine over cosine, so 0 over -1, that will be 0. The cosecant is 1 over the sine. The sine is 0, so this will be undefined. The secant is 1 over the cosine, so 1 over -1, so that will equal -1. And then the cotangent, 1 over the tangent, or the reciprocal over the tangent, so we can say if tangent is 0 over -1, this would be -1 over 0, so that's also undefined. And then part D, we're looking at when theta equals 3 pi over 2. This is 270 degrees. So now we're down here, the bottom. This is the coordinate point 0, -1. So let's go through one more time. Sine of this angle will be -1, the y-coordinate. The cosine will be 0, the x-coordinate. The tangent is sine over cosine, so -1 over 0, dividing by 0, undefined. So we were saying the tangent is undefined anywhere the cosine is 0, because you have to divide by 0. Then we have the cosecant. That is 1 over -1, because that's 1 over the sine. Sine was -1, so this will equal -1. Then the secant is 1 over the cosine, so 1 over 0. That will be undefined. And then the cotangent, when theta equals 3 pi over 2, is the reciprocal of the tangent, so 0 over -1. So that'll be equal to 0. So notice we get some undefined values for the quadrantal angles, and that's because some of the trig functions, sometimes the sine is 0, sometimes the cosine is 0. So anywhere where they appear in a denominator, we're going to get an undefined result. So we've already built out 4 points on the unit circle. And so I have a diagram. You can find something similar to this if you just search blank unit circle. I'll probably post something in D2L as well that you can print out. Or you can just draw a sketch. I used to just make my own circle. So let's put out what we know. We're going to slowly be building this throughout our time today. So for each of these, there's a spot for the degree measure and then the radian measure. So this is 0 degrees or 0 radians. We could also say 2 pi, but we'll leave it at that. And we said that's the point 1 comma 0. And then we have up here at 90 degrees, we've said that's pi over 2. This is the point 0, 1. Over here at pi, this is 180 degrees, negative 1, 0. So just plotting these points on this circle with radius 1. And then down here at 270 degrees, that's what we've been calling 3 pi over 2. This is the point 0, negative 1. So we get 4 nice points. And again, keep in mind, every xy coordinate point gives us the cosine and the sine of the angle that produced it. So with this in mind, let's come back here. I think we had another example in relation to coterminal angles. So coterminal angles, if you recall, let me jump back here, terminate at the same position. So they produce the same point on the unit circle. So any point that's coterminal, if we went around 10 times and then landed back up here, that angle would have all the same trigonometric values as just going straight there. So coterminal angles share the same trigonometric values. So let's take a look at these quickly. So our first is asking us for the sine of 3 pi. So we just have to think about where this would be. It's helpful to draw a little sketch. So here's our circle. And I know 1 pi is 180, so that would be 1 pi. Then 2 pi would bring us back to the starting point, so that's like 360. My pen kind of did a weird thing here. And then 3 pi would place us back at the same location as 1 pi. So they're coterminal. So we can say that the sine of 3 pi will be equivalent to the sine of pi. And that's something we do know. This is over here at the point negative 1, 0. And the sine of an angle, that's the y coordinate point on the unit circle. So we can say the sine of 3 pi should be equal to 0 because it lands on that same point. Another thing we can do, because notice it's more than 2 pi, so we've gone a full revolution plus some more. You can think about its coterminal angle by adding or subtracting 360 degrees, or in this case, 2 pi. Well, 3 pi minus 2 pi is 1 pi. That'll give you an idea of what your angle is coterminal to. If it was a really negative angle, you would want to add 2 pi until you get something positive, something that looks familiar. And those will be coterminal. So let's look at example B. We have the cosine of negative 270 degrees. Well, what would that be? Well, think of the positive angle, and then you just need to rotate in the other direction. So here's our circle. Positive 270 degrees, you would rotate counterclockwise, and that's down here. You move through 3 quadrants and then end on the axis. So you just need to make that same rotation in the clockwise rotation to make it a negative angle. So go through 1, 2, 3, and then end on the axis. So it'll end coterminal to 90 degrees, or pi over 2. So this is the point 0, 1. So we can say cosine of negative 270, well, that should be the same thing as the cosine of 90 degrees. They're coterminal. So they'll share trig values. And the cosine is the x coordinate, so this will be equal to 0. So the main point here is that coterminal angles share trigonometric values because they produce the same point on the unit circle. All right, so we found the quadrantal angles. Let's build out something else that we can figure out, and this is for 45 degrees. And previously we've said that that's pi over 4. If we're looking back at our chart, this whole thing is 90 degrees, so half of it is 45, and if that's pi over 2, half of pi over 2 would be pi over 4, dividing that by 2. A quarter pi. So how can we find out what the coordinate point should be? Let's think in terms of a triangle. So let's say we have our triangle within the unit circle that's produced by our point. So we can imagine this would be our point that we're interested in. This would be the origin. So that means this is the radius of the circle, which will be equal to 1. That's how we define the unit circle. And if this is a 45 degree angle, that would make this a 45, 45, 90. Because these two angles must add up to 90 degrees. So if one is 45, the other has to be 45. And this produces two equal side lengths since the angles are the same. So we can call this some distance x, and this would be the same thing, also x. Well, let's use the Pythagorean theorem to solve for x. We know that x squared plus x squared should equal 1 squared. A squared plus b squared equals c squared. So let's solve for x. X squared plus x squared will give us 2 of those, 2x squareds. 1 squared is just 1. I'll divide 2 on both sides, so x squared equals 1/2. Then I'll take the square root of both sides, and you should keep in mind when you do this, you need to introduce a plus or minus. So plus or minus root 1 over 2. But since we're in the first quadrant, we have an angle less than 90 degrees, we want to say that this is a positive x value and this will be a positive y value. So let's take the positive square root. And we can write this as square root of 1 over the square root of 2. The square root of 1 is just 1. So that means we can say x equals 1 over the square root of 2. And then you usually see this rationalized, meaning to rationalize the denominator, if you have a square root in the denominator, you want to multiply your fraction top and bottom by that root. So on the numerator, we'll have root 2. And on the denominator, the square root of 2 times the square root of 2, that's like squaring it. It's going to delete the square root. It undoes the square root. And that's what we want. That's the process of rationalizing the denominator. All right, and that's the value that we're looking for. This will be the value of both x and y for 45 degrees or for pi over 4. Because keep in mind those are equivalent. Pi over 4 radian. So let's make a little conclusion here. What this tells us is that each of these side lengths is root 2 over 2. This is also root 2 over 2. So that will be our coordinate point. We can say for theta equal to pi over 4, the corresponding point on the unit circle is root 2 over 2, root 2 over 2. Because that will be this distance here and this distance here. All right, let's add that to our circle. So let me jump back. So 45 degrees is here in the middle. We're saying that's equivalent to pi over 4 radians. And it will have this point root 2 over 2, root 2 over 2. So that one's easier to remember because the x and y coordinates are the same. All right, let's continue. So let's list out our trigonometric values for this. So we're saying theta equals pi over 4. So we can do a quick sketch. We just said this will have the coordinate point root 2 over 2, root 2 over 2. And again, the x is the cosine of the angle and the y is the sine of an angle. So we can just start listing these out. Notice the sine and the cosine will be equal for this angle. So the sine of theta, you can say the sine of pi over 4, is root 2 over 2. Similarly, the cosine of pi over 4 is root 2 over 2. Then the tangent, remember earlier we said the tangent is equal to the sine over the cosine of that same angle. So that means this will be root 2 over 2 over root 2 over 2. Looks messy, but you just have something over itself, so that'll just divide into positive 1. So the tangent of 45 degrees, or pi over 4, is equal to positive 1. Let's get the rest. So we have the cosecant, which is the reciprocal of the sine, meaning we would flip this fraction, so 2 over root 2. Well, let's rationalize the denominator, so multiply by root 2 over root 2. That'll give us 2 times root 2 over 2, and the 2's will cancel, so we'll just get the square root of 2. Might be easier just to remember that we said earlier the sign was actually 1 over root 2, so we're just flipping that. We ended up having to rationalize twice. Then we can do same thing for the secant. We would get the same value. Let's just take a shortcut, since we know that the cosine and the sine are the same. So the secant and the cosecant will also be the same. And in the cotangent is the reciprocal of the tangent. Tangent was 1, so cotangent will just be also 1. So we're using this point in order to list out the trigonometric values, just using those coordinate points. And notice we can kind of always relate things to the sine and the cosine, and that's part of why this is so useful. All right, now let's mix a few things together. So this is example 5. So looking at part A, we have the sine of 45 degrees times the cosine of 180 degrees. So 45 and 180. Let's just think about what those 2 points will be. So we have a circle. 45 we just said was root 2 over 2, root 2 over 2. And then 180 is over here at negative 1, 0. So the sine of 45 is positive root 2 over 2. So this should be equal to positive root 2 over 2 times the cosine of 180. Cosine is the x-coordinate, so times negative 1. So this result should be negative root 2 over 2. All right, let's look at part B. we're given the tangent of pi over 4 minus the sine of 3 pi over 2. So we're thinking about pi over 4 and 3 pi over 2. Well, let's draw another little sketch. Pi over 4, we just said earlier, was root 2 over 2, root 2 over 2. And 3 pi over 2 is down here at the bottom, so 0, comma, negative 1. But this time we're working with the tangent. So remember that tangent we defined as sine over cosine? So this would be sine of pi over 4 over the cosine of pi over 4 minus the sine of 3 pi over 2. So let's plug in what we have. Sine of pi over 4 is root 2 over 2. Cosine is also root 2 over 2. We saw earlier that the tangent was equal to 1 because these will cancel. And then we're subtracting the sine of 3 pi over 2, and sine is the y-coordinate, which is negative 1. So we're doing minus negative 1. Just got to be careful of that double subtraction. So this ends up reducing to 1 plus 1. Simplest of arithmetic, aka 2. All right, let's look at part C. And let me write it in, and then I'll scoot down. So we have the secant of pi over 4, and they take this quantity and square it. And then we add the cosecant of pi over 2. Notice there's no sines or cosines, but we can still relate these to the cosine and the sine. Let's first think about the angles. So we have actually those same ones. We have pi over 4, and well, this time it's pi over 2 instead of 3 pi over 2. So I'll do a quick sketch. Pi over 4 is root 2 over 2, root 2 over 2. And then pi over 2 is up here at 0, comma 1. So if we have the secant squared, well, the secant, remember we said was 1 over the cosine. So we can say this is 1 over the cosine of pi over 4, that quantity squared. And then we're adding to this the cosecant. We define that as 1 over the sine. This is 1 over the sine of pi over 2. All right, so let's just plug in our points now because we can relate this to the sine and cosine. So for pi over 4, the cosine is the x-coordinate, and we want the reciprocal, so this will be 2 over root 2 squared plus 1 over the sine of pi over 2. Sine is the y-coordinate there, so this will be 1 over 1. This will give us 4 over 2, because we squared the numerator and the denominator. 2 squared is 4, root 2 squared is 2, plus 1. 4 divided by 2 is 2, so 2 plus 1 is equal to 3. So again, just to show how we can locate the angles, think about their points, and then think about our other trig functions in terms of the sine and the cosine. So that was for 45 degrees. Let's do something similar for 30 degrees and 60 degrees. And that was, so 30 degrees we saw previously was pi over 6, and 60 degrees is pi over 3. So again, let's imagine a triangle that's produced by that angle on the unit circle. So some triangle. And let's say that this is our 60-degree angle. Well, that would make this 30 degrees because they're complementary angles. They need to add up to 90. So again, we're measuring, this is our point on the unit circle. This would be the origin. So this is our hypotenuse of 1. And then let's call this side length A and this side length B. So we need to be able to find out what these are. So a trick we can use is to mirror this triangle. Let's build another one here. And let's say that it's exactly symmetrical, even though it looks a little different. So that means that this is also 60 degrees and this is also 30 degrees. It's just a flipped version. Well, notice now this total angle is 60 degrees because each component is 30 degrees. So really we have built an equilateral triangle. This side length would still be A, this would still be 1, and we can describe this total side length as 2A, A plus A. Well, since in the larger triangle all the angles are the same, all the side lengths must also be the same. So that means this side length of 2A must be equal to 1. So let's just solve for A. You can say 2A equals 1, therefore divide the 2 over, A equals 1/2, and we get our first important side length. So A equals 1/2. So let's find the other one. Now let's sort of zoom back into a single triangle and use the Pythagorean theorem. Since we know that A squared plus B squared should equal 1 squared. And we just said that A was 1/2. So we can say 1/2 squared plus B squared equals 1. 1/2 squared is 1 over 4. So 1/4 plus B squared equals 1. Let's jump up here. We'll subtract the 1/4 over. So B squared equals 1 minus 1/4. Now we're subtracting two fractions. Let's get a common denominator. That 1 we can view as 4 over 4 minus 1 over 4. So we're saying B squared would be 3 over 4, or minus 1. Subtracting two fractions, keep the denominator the same once we've found a common denominator, and then we can add or subtract the numerators. And then we'll take the square root of both sides. So similarly, we get a plus or minus, but we'll take the positive version since we're still in the first quadrant, since this is just a 60-degree angle, so it's less than 90. So we would expect the y value, this vertical distance, to be positive. That's what we're describing as b. So just need to simplify this. We can take the square root of the numerator over the square root of the denominator. So I'll say b equals the square root of 3. We'll just leave it as that. And then the square root of 4 is 2. So here's our second important angle, or side length, I mean. Root 3 over 2. So let's build a new triangle just to show these side lengths. So again, we're in the unit circle, just showing the triangle. This is 60 degrees. Remember, 30 degrees was pi over 6, and 60 degrees was pi over 3. And you can run those conversions again if you need to. So this was our 60-degree angle, so this will be pi over 3. And this is our 30-degree angle up here, so pi over 6. And then we have said hypotenuse is 1. This was our side length A, so 1/2. And then this is our side length B, root 3 over 2. This will give our x and our y coordinate of the associated point on the unit circle. So let's define the sine and the cosine for each of these, because that'll be what we're interested in. So we can say when theta equals pi over 3. That's our 60-degree angle. The sine is opposite over hypotenuse, so opposite over hypotenuse, or we can see this will be the y-coordinate of the point that we'll build. So we can say the sine of theta when theta equals pi over 3 is root 3 over 2. And then we can say the cosine is adjacent over hypotenuse, so 1/2 over 1, or just 1/2. That means for pi over 3, or for 60 degrees, we'll get the coordinate point 1/2 root 3 over 2. But let's also look from the pi over 6 perspective, because we can answer that while we're here. So let's say when theta equals pi over 6, now the opposite is 1/2, so the sine will be 1/2. Notice the sine becomes the cosine value of the complementary angle. And that's what we saw. That was a property of these co-functions. So the sine of theta for pi over 6 is 1/2. And then the cosine is root 3 over 2, because that'll be the adjacent over the hypotenuse. So the points just flip. So this will be the coordinate point root 3 over 2, positive 1/2. So we actually now have our full first quadrant. Think about quadrant 1. So let me put just the positive x and y axis. So here's our unit circle slice. So we already know we have the point 1, 0 here and 0, 1 here. Right in the middle was 45 degrees, or pi over 4. That's the one that has the root 2 over 2's. And then up here, this is the higher one. So this is 60 degrees. We said that will have the point 1/2 root 3 over 2. And then down here, 30 degrees, or pi over 6. The same numbers here, but just flipped in order. So it'll be root 3 over 2, 1/2. So this is already a lot of progress on our unit circle, and I'll show in a moment how if we can have this slice, just this first quadrant memorized, this is where a bulk of the memorization task will be, we're able to get all of the other special points on the unit circle just based off of symmetry, just based off of knowing that things are symmetrical around a circle. So notice there's only a few numbers to memorize here. You can get the 2 quadrant angles pretty easily. Just remember you're on a circle of radius 1. And then the other numbers are like root 3 over 2, 1/2, or root 2 over 2. Might be helpful that the one in the middle, where it's even for pi over 4, it's the same thing, root 2 over 2, root 2 over 2. So the double 2's might be helpful. And then when I was memorizing this, it can be confusing. Should I say 1/2 root 3 over 2 or root 3 over 2 1/2? I just memorized that it starts on top with the 1/2, with the thing that does not have a square root. So that could potentially be helpful. And then the other one down below is the same coordinate point, but just with the x and y flipped, because they are complementary. So we have our first quadrant. So let's write out our trig values for these. So for pi over 3, let's just quickly run through this. So pi over 3, that's 60 degrees. Okay, I know that is this upper one that starts with 1/2. And the other coordinate point is root 3 over 2. So the sine is the y-coordinate. That's root 3 over 2. The cosine is the x-coordinate. That'll be 1/2. The tangent, and this is when theta equals pi over 3. The tangent is the sine over cosine. So our sine value is root 3 over 2 divided by the cosine. I'm going to write it out like this, divided by 1/2. So we'll see that we're doing a division of two fractions. So when I do that, dividing two fractions, I'll keep the first one, change division to multiplication, and then flip the second fraction. And then notice these 2's will cancel. So we'll just get the square root of 3. So that's the tangent of pi over 3. Now the cosecant, that's the reciprocal of the tangent. So this would be, instead of root 3 over 2, 2 over root 3. And then we'll just want to rationalize. So let's multiply by root 3 over root 3. So that'll give me 2 root 3 over 3. Then the secant is the reciprocal of the cosine. So instead of 1 over 2, it'll be 2 over 1, or just 2. And then the cotangent is the reciprocal of the tangent. So instead of root 3 over 1, I can say 1 over root 3, and then rationalize. And I'll get root 3 over 3. So these are the exact values. Keep an eye out for when they ask for the exact values. It means they want these particular forms with the square roots. Because we could just in our calculator type in the sine of pi over 3, and it'll give you a decimal. It'll give you some decimal. And that might be good enough for some application problems, but oftentimes we're looking for these exact answers. We want to try to practice using the unit circle to bring up in our memory these coordinate points in order to know what the values are without having to type them into a calculator. That's our ultimate goal. All right, let's quickly do the same thing for pi over 6. And a lot of these will be similar. So pi over 6, that's 30 degrees, that's the lower one. So that's the one that starts with the square root of 3 over 2. Then we have 1/2. All right, so we're saying when theta equals pi over 6, we're looking at 30 degrees. Oops, pi over 6. This time the sine is 1/2. The cosine is root 3 over 2. The tangent, sine over cosine, so let's write that out again. This time the sine is 1/2, and we'll divide by root 3 over 2. So that means we're doing 1/2 times 2 over root 3. So these 2's will cancel. So we get 1 over root 3, or if we rationalize, if we remember from last time, that gave us root 3 over 3. Now the cosecant is reciprocal of the sine, so 2 over 1, or just 2. The secant is reciprocal of the cosine, so 2 over root 3, and let's rationalize, so 2 root 3 over 3. Not writing that intermediary step just because we did that earlier. And eventually you'll get sort of used to this rationalization pattern. And then the cotangent is the reciprocal of the tangent. So let's use this version before we rationalized. So instead of 1 over root 3, we can say root 3 over 1. Let's skip out that middle step. Or just root 3. So notice again, we get all of these just by knowing the coordinate point, by knowing the x and y coordinate point on the unit circle. So I mentioned we're able to get everything after knowing the first quadrant. Let's first fill out the first quadrant here. So we just said for 60 degrees, this is pi over 3. For 30 degrees, this is pi over 6. And we said for pi over 3, it starts with 1/2, and then we get root 3 over 2. And then for pi over 6, starts with 3 over 2, and then 1/2. So these two just have flipped coordinate points. So that's our first quadrant. So let's first focus on the second quadrant and think about the symmetry of what's going on. So notice that these points each have a pair in the second quadrant that exist on the same horizontal line because it's symmetrical. We can imagine like a mirror going down the y-axis. So if they're on the same horizontal line, well, they must have the same y-coordinate. And if it's symmetrical around here, it would be the same distance just in the negative direction. So they must have the same x value, but the value will be negative instead of positive. Just think about if you were plotting a point in each coordinate, each quadrant, and what would be positive, what would be negative. In the first quadrant, x is positive, y is positive. In the second quadrant, x is negative, y is positive. In the third quadrant, both x and y are negative. And then in the fourth quadrant, x is positive, y is negative. So we can really just steal these 3 points, the values that they have, and then just change positive to negative, negative to positive, depending on which quadrant we're in. Meaning that this would now be negative 1/2, positive root 3 over 2. This would be negative root 2 over 2, positive root 2 over 2. So the same middle point, just with the x value negative. Then this would be negative root 3 over 2, positive 1/2. Now what about the angles? So notice we have pi over 3, pi over 4, pi over 6. Well, there'll be a similar pi over 3, pi over 4, pi over 6 angle in each quadrant. The one that's closest to the y-axis will be our pi over 3, and I'm going to leave a little space. The one in the middle is your pi over 4 angle. So if you see a pi over 4, that's your giveaway. It's going to be one of your root 2 over 2s. And then the one closest to the x-axis is your pi over 6 angle. And the general pattern in the second quadrant is that you'll see a number in the numerator that's 1 less than the denominator. So by that I mean this will be 2 pi over 3, this will be 3 pi over 4, and this will be 5 pi over 6. And in terms of degree measure, this is 120 degrees, in the middle is 135, and then this is 150. So let's keep going with this symmetry and the patterns. We mentioned in the third quadrant, everything's negative. X is negative, and y is negative. So I'm just going to borrow these same points again and make everything negative. We'll start here. These will be like pairs together. So I can say this will be negative root 3 over 2, negative 1/2. Because now these exist on the same vertical line. They should have the same x value, and then the y value will be the negative version. So let's continue. This will now be in the middle, negative root 2 over 2, negative root 2 over 2, everything's negative. And the one down here will be negative 1/2, negative root 3 over 2. Now what about the angles? We're still going to have a pi over 6 angle close to the x-axis, a pi over 4 angle in the middle, and a pi over 3 angle close to the y-axis. Now here, instead of the numerator being 1 less than the denominator, the numerator is 1 more. So this will be 7 pi over 6, this will be 5 pi over 4, and this will be 4 pi over 3. And this is associated with 210 degrees, 225 degrees, and 240 degrees. All right, we're almost there. Just need the fourth quadrant. So let's continue our pattern. In the fourth quadrant, x should be positive, and y should be negative. We're now on same vertical line, so the x values should be the same, and then the y values should flip in sign from positive to negative. So down here will be positive 1/2, negative root 3 over 2. Then we should get positive root 2 over 2, negative root 2 over 2. Then this would be positive root 3 over 2, negative 1/2. And then in a similar way, we'll still have a pi over 3 angle, we'll still have a pi over 4 angle, and we'll still have a pi over 6 angle. Now the pattern here is a little bit more weird. If you take the denominator, multiply it by 2, and then subtract 1, you'll get the number that you'll see in the numerator. So looking at this first one, 3 times 2 is 6, minus 1 is 5. It'll be 5 pi over 3. In the middle, 4 times 2 is 8, minus 1 is 7. And then here, 6 times 2 is 12, minus 1 is 11. And then this will be associated with 300 degrees, 315 degrees, and 330 degrees. So each quadrant has like a 30 degree, 45 degree, 60 degree angle, or a pi over 6, a pi over 4, a pi over 3 angle. You just have these different patterns for the numerators. So I use all of this, like for example, you might be asked, well, what is the sign of 2 pi over 3? Well, if I have the first quadrant memorized, that's where I mentioned the bulk of the memorization should be. I know it's going to be related to a pi over 3 angle. So I know for pi over 3, the sign is root 3 over 2, but the question is, should it be positive or negative? Well, if I look at the angle and I see, okay, it's 2 pi over 3, it has that pattern, the numerator is 1 less than the denominator, that means I'm in the second quadrant where y is positive. So that means the sign should be positive. So I can take the positive version of its associated pi over 3 angle. And we can do that with each of the angles in the different quadrants, as long as you can recognize the pattern and what quadrant you're in, what should be positive and negative. If you have just the first quadrant memorized, you can steal those points and then assign the particular positive or negative sign that's needed. So that was my method. When I was learning this, I was pretty intimidated by memorizing this whole circle. But if you start with just the first quadrant and then utilize the symmetry and the patterns, you can kind of get the rest of them for free, or at least with less mental space taken up. So I would suggest maybe once per day for 2 weeks, try to recreate the unit circle. Maybe the first few days, try to just memorize and recreate the first quadrant. Then as you move forward, once you have the first quadrant down, try to get the symmetry of the other 3 quadrants, because the bulk of the work will be in that first quadrant. And it'll take some time, but it'll pay off. So this skill will be with you through pre-calculus and calculus and beyond. You'll be able to have these values ready to go in your mind. That'll give you a big advantage. So it'll take some effort now, but I promise it will pay off in time. All right, let's look at a few more examples and how we can use this. That'll hopefully give some more context. So here we're looking at multiples of pi over 4. So let's look at our first example. We have the cosine of 5 pi over 4. So I'm going to demonstrate how I use this sort of technique. So 5 pi over 4, I see the pi over 4, so it must be, one of the root 2 over 2s. It's related to that middle point in the first quadrant. But it's 5 pi over 4. I see the numerator is 1 more than the denominator. So that means we're looking at the 45-degree angle, the pi over 4 angle, in the third quadrant. And we're in the third quadrant, so everything should be negative. This should be negative root 2 over 2, negative root 2 over 2. And I want the cosine. I want the cosine of 5 pi over 4. And I know the cosine is the x-coordinate point. So that will be negative root 2 over 2. So I'm just trying to imagine, based on patterns, which quadrant am I in, and which point in the first quadrant does it relate to? Is it a 30-degree angle, a 60-degree angle, or a 45-degree angle in its respective quadrant? Let's see another example. So now we have the sine of 135 degrees. Well, if we did a quick conversion, 135 degrees, that's equal to 3 pi over 4. So 3 pi over 4, the numerator is 1 less than the denominator. That's the second quadrant pattern. So in the second quadrant, the x is negative, so this would be negative root 2 over 2. And now the y is positive, positive root 2 over 2. And I'm looking for the sine. So the sine is the y-coordinate point, positive root 2 over 2. So I usually do a quick little sketch, think about the coordinate point, and then steal the value that I need. Or maybe we need to modify it if we're looking at one of the other trigonometric functions. All right, let's look at part C. C asks for the tangent of 315 degrees. Well, let's translate again. So 350 degrees, 15 degrees. If I want to convert to radian, I multiply by pi over 180. Let me reduce that in my calculator. So 315 over 180 will reduce to 7 pi over 4. Okay, 7 pi over 4, 4 times 2 is 8, minus 1 is 7, that's the fourth quadrant. So I'm down here. So this would be the coordinate point. In the fourth quadrant, x is positive, so positive root 2 over 2. Y is negative, negative root 2 over 2. And I'm looking for the tangent. So the tangent of 315 will be the sine over the cosine. The sine is the y-coordinate point. You can already see this will simplify to negative 1, because I have negative root 2 over 2 over positive root 2 over 2. This will equal negative 1. All right, let's keep going. We can even consider negative angles. So let's say for D, sorry, getting a little messy here. I'm looking at the sine of negative pi over 4. Negative angle, but what is that coterminal to? Well, positive pi over 4 would be up here in the first quadrant. Negative pi over 4 would just rotate that same amount in the clockwise direction. So it's down here in the fourth quadrant. So it's actually coterminal with the same point. So let me just steal that coordinate point. and I'm looking for the sign. So the sign is going to be the negative value. It'll be the y coordinate. The sign should be negative in the fourth quadrant. So I'll just go ahead and say this should be equal to negative root 2 over 2. All right, let's make this look a little nicer. All right, last we have the cosine, this is part E, the cosine of 11 pi over 4. Well, this doesn't meet any of our patterns. It's not in, can't tell which quadrant it's going to be in, but it's more than one full rotation around. So let's just try to count in pi over 4s and see where we are coterminal to. So pi over 4 is 45 degrees, so we'll get 2 pi over 4s per quadrant. You can imagine 1 pi over 4, 2 pi over 4, 3 pi over 4, 4, 5, 6, 7, 8, 9, 10, 11. This will end us up over here. So we terminate in the second quadrant. So it'll be coterminal with our angle from B with 3 pi over 4. So in the same way, we can just steal this coordinate point. And the cosine is the x value. So since we can say 11 pi over 4 is coterminal with 3 pi over 4, it'll share the same value. So the cosine of 11 pi over 4 is equal to negative root 2 over 2. That's the x value up there. All right, got a little messy here, so apologies for that. But this is just to demonstrate, and this was all for our pi over 4 angles, so angles in the middle of the quadrants. But I just visualize which quadrant I'm in using the patterns of the angles, and then think about what should be positive and what should be negative. And that's how I can deduce what the values of these trig functions will be. All right, in example 10, they do a similar thing, but for 30-degree or pi over 6 angles and pi over 3 angles. And they already have them worked out, so you can work through these on your own. Just to give a couple examples of the visualization, like for part A, we're looking at the cosine of 7 pi over 6. Well, it's a pi over 6 angle, and those are closer to the x-axis. That's like your 30-degree angle in the first quadrant. And I see I have 7 over 6, so numerator is 1 more than the denominator. So that's the pattern for the third quadrant. So I should be this angle that's closer to the x-axis in the third quadrant. And that would have both of the values will be negative. So this would be negative root 3 over 2, negative 1/2. I'm relating it to the pi over 6 angle up here that was positive root 3 over 2. Sorry, I have to write a little small, positive 1/2. But I'm over here in the third quadrant. The cosine is the x value, so notice they said the cosine is negative root 3 over 2. Let's just do one more just for the sake of example. So for B, we're looking at the sine of negative pi over 3. Well, positive pi over 3, the pi over 3 angles are closer to the y-axis. That would be positive pi over 3. So negative would just be down here. Positive pi over 3 starts with the 1/2. So 1/2 root 3 over 2. So the negative version, the x will still be the same, but I'm in the fourth quadrant now, so my y coordinate should be negative. So 1/2 root 3 over 2. So, or 1/2 negative root 3 over 2. So the sign must be this negative root 3 over 2. That's the y coordinate. So just to give some examples. So you can use that same idea. Look at the pattern in the angle, identify which quadrant you're in, and then relate it to the similar angle in the first quadrant. They use the term reference angles for these. That's what they mean by that. We're referencing something we know from the first quadrant. All right. The next section just has you practice using a calculator to find values. We have all of these nice special angles on the unit circle, but oftentimes in practice, you get angles that fall in between these. This is more of like a perfect situation. So in application problems, you'll often run into angles that aren't your nice special angles. So that involves having to plug them into a calculator. So just keep in mind, if you're working on a homework problem and you see this, like express your answer rounded to a certain number of decimal places, that's a giveaway that you're going to be plugging into a calculator. So just as a heads up. If they say give the exact value, the exact means you want to use the unit circle to get some value involving square roots. So try plugging these in. I'll just make a special note. Check if your calculator is in degree or radian mode before plugging in. So check if your calculator is in degree or radian mode. So if you see the little degree sign, that means you're plugging in degrees. You want it to be in degree mode, so it gives you a correct result. If you see something with pi, that is a giveaway that you are in radian mode, or if they say specifically these are radians, just be sure your calculator is in radian mode, because if it's in degree mode and you input radians, it's going to give you an incorrect result. So just keep that in mind. You may think you're doing the right thing, but you're just in the wrong mode in your calculator, and that can be pretty annoying because you're trying to plug into the homework questions and keep saying you're incorrect. Just speaking from experience. All right, we will finish this off just sort of expanding our view a little bit. And let's say we want to imagine we're no longer on the unit circle, but we're on some circle of radius r instead of radius 1. We can use similar logic. We're still centered at the origin, but now instead of a radius 1, it's a radius of r. And now let's think about, well, what would our coordinate points be? Well, this would produce some x value and some y value. This is still our angle theta. So let's say this is x and this is y. Well, the sine of theta is opposite over hypotenuse. So we can say, let me do this on the side. We would say something like the sine of theta this time is y over r. Notice that's what they show here. So if we wanted to solve for y, to say what is the y coordinate, well, we would have to multiply this r over, and we would say y equals r times the sine of theta. And we'll get a similar thing for the cosine. It would be r cosine theta for x. So that means a coordinate point on some larger circle would be r cosine theta for the x value and r sine theta for the y value. In our specific example with the unit circle, our r value was 1, and that's what produced that really nice result that the x coordinate is just straight up the cosine, the y coordinate is just the sine. That's part of why the unit circle is so valuable as a mathematical object. But we can imagine we're farther away from the origin. So let's look at a question involving this sort of thing, and I'll show you my particular method for solving it. This says, find the exact values of the 6 trigonometric functions of an angle theta if 4, -3 is a point on the terminal side in standard position. So that means we have some circle, don't know the radius, it's centered at the origin, but imagine the point 4, -3. So that would be somewhere, we'd have some distance of 4 and then some negative distance of 3. And then we can imagine producing a triangle like this, where this would be our angle. Or maybe our angle is going all the way around. Either way, if it's coterminal, we can think of it producing a triangle like this. So let's look specifically at this triangle. So yeah, if this is the point 4, -3, that means this side length we can say is 4, and this side length, let's say, is -3. It might feel weird to describe a side length of a triangle as negative, but since we're in this sort of mindset of being in a certain quadrant, it can make a little more sense, and it will actually give us the correct trig values. So if we can find out what the radius is, then we can just use SOHCAHTOA on this angle to answer all of our trig function values. So that's what I would suggest. Let's first find this missing radius via the Pythagorean theorem. So 4 squared plus -3 squared will equal r squared. 4 squared is 16. -3 squared is 9. 16 plus 9 is 25. So let's take the square root of both sides, and we'll say r equals 5. Technically plus or minus 5, but for the radius, just go ahead and use the positive value. So we have our 3 lengths of the triangle. It's a 3, 4, 5 in a way, 3, 4, 5 triangle. So let's just use SOHCAHTOA to list out the values. Remember, sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So let's just list it out. The sine of this angle, whatever it is opposite over hypotenuse, so -3 over 5. The cosine is adjacent over hypotenuse, so that will be 4 over 5. The tangent is opposite over adjacent, so that would be -3 over 4. The cosecant is the reciprocal of the sine, so let's just flip it. -5 over 3. You can just stick the negative up top. The secant is the reciprocal of the cosine, so 5 over 4. And then the cotangent is the reciprocal of the tangent, so -4 over 3. So pretty easy once we've built this triangle. So that's what I would generally suggest. If you're given a problem like this where your point is not a coordinate point that you're used to seeing on our standard unit circle, just build out a triangle. Think about what's positive and what's negative, what your direction should be. This was a +4, so we want to go in this direction, and then down -3. From that perspective, we get a nice triangle. You can solve for the unknown radius using the Pythagorean theorem, and then get your trig values via good old SOHCAHTOA. So I would suggest this triangle method, and we'll see this come up in some other forms later. All right, so this was a big section. The main thing that we built up to was building out this whole unit circle, and then we started to answer some of these questions using the unit circle to find some trigonometric values. So again, I would suggest just start with trying to memorize the first quadrant. Try to just notice what you can here. It's not too many values, 1/2, √3 over 2, √2 over 2, just got to place them in the right position. And then we have our pi over 3, pi over 4, pi over 6. So try to get that down. And then use symmetry and the angle patterns to pull up the rest of the quadrants in your memory. So I would recommend practicing that once per day. All right, again, it was a big section. So we covered, we skipped to here, defining the exact values of the trig functions on our quadrantal angles. Well, we generally talked about what the unit circle was and what a point on the unit circle represents. We found the exact values of our pi over 4 trig functions. We did the same thing for pi over 6 and pi over 3. And we went around the unit circle, used some patterns to find all of our remaining points. You can practice using a calculator, plugging things in, and then we expanded beyond a circle of radius 1. So just use that triangle method to solve for something with a larger radius. All right, we'll stop this video here, and I'll see you next time.